Hello, and welcome to part two of the review of the periodic table. Um, we're going to continue discussing history because it's very important to have a good understanding of how the periodic came to be. From this point on in the timeline, we're going to go into the 1500s. The difference between part one and part two is that everything from this point on, all the theories of the atom, were now based on experimentation and observations. In other words, how the theorists or the scientists came up with their theories from this point onward is they they had a question. Basically, the question is what is the structure of the atom? How can we come up with the structure of the atom? So based on this question, they came up with experiments. Then they conducted the experiments, looked at their observations, and based on their observations, they came up with theories that would help them explain the observations and further explain um, the structure of the atom and lead to more testing. So the first scientist we're going to talk about is Robert Boyle in around 1600. Um, his main contribution to science and chemistry was he experimented with gases, and he was interested in the behavior of gases. Uh, he found out that particles can be compressed, and if you compare compression of gases to liquids, gases are a lot easier to compress. He also believed, just as Democritus suggested in 4000 BC, that tiny particles make up substances, and these they would group together to make different substances. Boyle's law describes Robert Boyle came up with something called Boyle's law, which describes the relationship between pressure and volume of a gas if the temperature is not changing in a closed system. We talked a little bit about this in Science 8, but you're going to develop it a little bit more in further science courses. Um, and that's Robert Boyle's contribution. Um, yeah, this is actually pretty important to mention. Um, Boyle was convinced that matter was made up of tiny particles, and as was said in the earlier slide, this is the same assertion or the same suggestion or the same idea that Democritus had. So what's the difference between them? The main difference is this: Robert Boyle came to his conclusion because he based it on scientific observation. Okay, he conducted experiments. He had a question. He conducted the experiment. He made observations, and based on those observations, he came up with the theory. Whereas Democritus did not do this. Okay, so this is the difference between the philosophers and the scientists. And it's important to understand. It's one of the key questions you need to be able to answer that were given to you at the very, very beginning of part one. Antoine Lavoisier, 1770, 1780, in that time period. This person, this is credited with uh, being the father of modern chemistry. He began to investigate chemical interactions in 1770. Around 10 years later, he came up with a way to name the chemicals, which was important to do because scientists can now use the same words to describe their observations. Okay, so now we're going to get into the meat and potatoes of part two of the periodic table review, and we're going to talk about atomic theories. You need to know all of the theorists, and you need to know what their idea of the atom was. So the essential question is, how is the atom organized? Okay, again, I put this slide in because you have to understand that these theorists made their theories based on observations. So here's a quick look at all the theorists that we're going to be discussing, that we have already discussed. Um, uh, Everyone from Dalton to Rutherford and to Bohr's and Niels Bohr, and of course to the most recent conception of how the atom looks like, the quantum theory. So we're going to look at every single one of these theorists and have a look at what they think the atom is composed of and how it's composed. More importantly, how it's composed. Well, also what makes up the atom. So what are all these guys going to talk about? What are we going to learn about? First of all, we have to know what the atom is. The atom is the smallest part of an element that represents that particular element. In other words, the atom is the smallest part that makes up the element. So for example, if we're talking about the helium element or hydrogen element, copper element, whatever element it is you're talking about, each one of those individual elements are made up of specific atoms. So for example, a helium element is made up of helium atoms. Copper element is made up of copper atoms. That's what's meant in this first statement here. Okay, that they are of a particular element. You're going to see this being repeated over and over again, this part here. It's important to know, but every atom is made up of three major constituents, or three major things. The first one is an electron, which, as you can see here, has a negative charge. The other is what a lot of people think is the counterpart of the electron, is a proton, which has a positive charge, and you have a neutron, which is neutral. Okay, so it's neither positive nor negative. And protons and neutrons are considered right now to be located in the nucleus, and electrons typically are thought to orbit the nucleus. Now, this does not reflect all of these theorists' ideas of what the atom looks like, and we're going to learn a little bit more about that. Okay, so this is not everybody's theory. John Dalton is the first one we're going to talk about. In 1808, he suggested that matter was made up of tiny particles called elements. He was the first to define an element as a pure substance. He established the first modern theory of the atom. Each element is composed of a particle called an atom. An element is a pure substance because the element is made of a particular type of atom only. In other words, a gold element is made of gold atoms only. John Dalton explained the atoms as tiny solid balls, almost like billiard balls. Sometimes Dalton's atomic model is referred to as the billiard ball model. J.J. Thompson, 1897, is our next theorist. He continued from Dalton's work, and he discovered this first subatomic particle called the electron. Okay, so the word subatomic here, right here, all that means is, if you look at the word sub, means below, right? Like submarine, subway, right? Just below the surface. And all that means is, in this context, is that it's smaller. Okay, so he discovered a particle that was actually smaller than an atom, and he called it an electron. He proposed that the atom was a positively charged sphere in which negatively charged electrons were embedded. So his theory oftentimes is called the raisin-bun model. Okay, and the reason why it's called the raisin-bun model is because he believed that the electrons were just sort of embedded into a positive area. Okay, just like the raisins in the bun and the chocolate chips in the chocolate chip cookie. So that's why it's called the raisin-bun model. I'm not going to talk too much about this slide. All I'm trying to show here is that what we're going to be thinking about the electron. This is not what Thompson suggested at all. Okay, Thompson suggested that the atom is going to look something like this, where you have, the whole atom is going to be positive, and then every so often you're going to have, these negatively charged particles just kind of embedded sporadically within it. Okay, so this is what Thompson suggested. This is not what Thompson suggested, but this is what we're going to be thinking of, and I just wanted to quickly put that in, um, just to let you know. Okay, next theorist we're going to talk about is Nagaoka in 1904. And he suggested that the atom was like a mini solar system. Negatively charged particles orbited, in other words, they go around the nucleus. And at the center, which is the nucleus, was a large positive charge. The negatively charged particles went around the positive center, just like planets go around the sun. That's why he called it a mini solar system. Okay, and this is what Nagaoka's model would look like. Here you have a positively charged center, and you have all of these electrons that kind of go around it, just like planets, in our solar system going around the sun. Next theorist, this is a Canadian contribution, Rutherford, 1898 to 1907, and he suggested that the atom was mostly empty space. So if we just think about Nagaoka's model, Nagaoka did not talk about space. Okay, so there's some similarities between Rutherford and Nagaoka. For Rutherford, at the core was a positively charged center called the nucleus, just like Nagaoka. The nucleus contains protons and neutrons. So Nagaoka did not talk about protons and neutrons. He just said the center was positive. The nucleus is 1/10,000th the size of the entire atom. So the nucleus was very, very small. And a really good analogy, kind of a classic analogy to put things into perspective so that we can understand just how small the proton is compared to the rest of the atom, is that if you were to put a single frozen pea at the center of a big football field, that would be the relative size. So the pea would represent the atom, and the football field would represent, or the football stadium would represent the atom, the rest of the atom. Okay, so here's a picture for you. So here you have, I think this is the New England Patriots stadium. So the nucleus is like a green pea at the center of this field. So if you will put right there, right here, like, well, okay, that didn't work, but like a pea, that would be the relative size of a proton compared to the rest of the atom. So it just gives you a really, really good idea of how small it is. And to even consider it, electrons are even smaller. So how did Rutherford understand? Okay, why did Rutherford go out and say, okay, the atom is mostly empty space? Well, it's because he did an experiment. Okay, and of course there was a positively charged center. He based it on observations from an experiment, and this is his experiment. So what he did is he took positively charged particles, okay, and he just accelerated them and shot them into a gold foil. Okay, so if the atom was not empty space, then the high-speed particles just collide into the gold, and that would be the end of it. But that's not what he observed. Okay, what he observed is that most particles actually just went through the gold foil. But every once in a while, he would notice that the particles that were accelerated into the golden foil would not be projected into this background here. So he would just analyze the pattern, like on this film in the back here. I know this is actually, I'm not doing it really. Okay, like this part here is like how can I say it? It's almost like a screen, right? And he would just analyze where the particles would be embedded. So he would predict, because it was just empty space, that this particle traveling, would just continue on this trajectory and would be found right there. And for most of them, that's what happened. But for some of them, he observed that it deflected. Well, that's why he says that at the center, it's positively charged, because if you have a positively charged particle being accelerated towards another positively charged particle, well, the positive is going to repel from the other positive, and that will cause it to deflect. So that's how Rutherford came up with the idea that the atom is mostly empty space and also had a positive area, or a positive nucleus, I should say, in the middle. So this is just another sort of picture that I got from a colleague that shows the Rutherford's experiment. Okay, so again, a beam of positively charged particles are rushed through thin gold foil, and most of them are undeflected, but every once in a while you get something that is deflected and they pass through. So that supports the idea that it is mostly empty space, the atom is mostly empty space, and the idea that at the center is a positively charged nucleus. Niels Bohr. So this is going to be the model that we follow, because we're going to have to be able to draw some Bohr diagrams, and I'll show you that next in part 3. So he said that electrons orbit the nucleus in circular orbits called electron shells. So what's the difference here? Bohr is saying is that you're going to find electrons in specific areas going around. And they rotate around the nucleus randomly. And they can move from these areas from shell to shell by gaining or losing energy. So Bohr suggested that there are valence electrons, and so what that means is that for every shell, okay, so here's a shell, right? Here's a shell, here's a shell, here's another shell. These are all shells. I tried to draw this out a little neater, but that's the best I could do. And for every shell, there's going to be a maximum number of electrons that you're going to find. Okay, we'll do an example of how to draw a Bohr diagram in the next slideshow. James Chadwick, he discovered that the nucleus has positively charged particles called protons and neutral particles called neutrons. So Bohr discovered his contribution was based on his observations that there are specific shells that you're going to find the electrons. Chadwick went and said that the nucleus is made up of a positive particle called a proton and a neutron. Okay, so that was his contribution. Today, the model that's supported is called the quantum model, and the quantum model states that the atom has the nucleus, but the electrons are actually more found in a cloud, as opposed to valence shells. Okay, so this was a long video, but that's the end of it. So that's the end of part 2.